Thank you very much for the invitation and for giving me the chance to speak here. Well, I divided my talk in two parts. One part is a mathematical part, since I am officially a mathematician employed by a physics department, so this talk doesn't exist, because I would get my funding cut out if they would discover I'm doing still mathematics. And so basically I'm an algebraic quantum field theorist, at least at the moment. So one of the things I try to work with is the algebraic approach to quantum field theory and to apply it to cosmology. So from the mathematical point of view, if you think about quantum field theory, from algebraic quantum field theory on a cosmological manifold, the first thing you would ask is, okay, does it make sense to quantize a field theory on a cosmological space-time? And for quantizing, I mean, can you give me, so you give me a field theory, classical field theory, and then I build, let's say, a model, a quantum model out of this classical field theory, which means I give you an algebra of observables and a state out of which you can compute explicit expectation values. This well, basically is the motivation for the first of the two talks, since I suspect that not many of you are familiar with algebraic quantum field theory. Above all on curved backgrounds, I will basically tell you the basic ingredients, so the ABC of the theory. Then I will show you that giving an algebra of observables on basically any globally hyperbolic space-time for a free field theory is a trivial exercise for students. On the other hand, assigning a quantum state is the key problem of any quantum field theory on a curved space-time, and till, well, 2005, only two quantum states were explicitly known on curved space-time. That means the Poincare vacuum and the Bunch-Davies state. Any other state which was out there could be proven not to be physically meaningful, because it could be proven that there were at least a bunch of observables whose quantum fluctuations were not bounded on this state. So those were the only two called physical states which were known in the literature, and it has been lately developed a technique to construct explicitly states of physical interest, which means that they mimic the ultraviolet behavior of the Poincare vacuum, and all quantum observables have bounded fluctuations by means of basically a novel application of the so-called holographic principle, if you want to be fashionable, or if you don't want to be fashionable, basically you embed your algebra of observable in a larger algebra by means of a star homomorphism, and this larger algebra, for various reasons I will show you, is nicer in the sense that it's much easier to assign a state to this larger algebra, which you can control and whose physical properties could be studied at ease, and then you restrict it to the smaller algebra, the physical algebra, and you know that your state, even when restricted, is physical. And I will try to do it particularly for cosmological space-times, and what I will tell you in the first talk is based on these two papers I've written a few years ago with Walter Moretti from Trento and Nicola Pinamonti. At that time we were both in Hamburg, now he's in Genoa. And the second remark I want to do is that besides these motivations, there is another reason I wanted to study these states, and namely, one thing people from AQFT are often criticized for, and I think there is a good point even in this criticism, is that we are not able to give real numbers. So my colleague next door is an experimental physicist, and he tells me, can you give me a number I can measure? And that's one, well, let's say, a bad point of formalism which wants to study quantum field theory, which is very well known for its experimental successes. And that's so one thing we wanted to do was like, okay, let's try also to build a model, a quantum theory, which has physical implications, which in principle could lead to measurements and experimental falsification of the model. So that was the long goal, but about this I will talk in the second part in the second talk. So I will start with something easy, so that I will start with the cosmological principle, which basically tells us that the background we are working with is foliated by a Cauchy surface, which I call sigma, which is a homogeneous three-dimensional manifold, topologically either a sphere, a plane, or a paraboloid, whereas I is an open interval of the real line, which is here called the cosmological time. If you assume that the space-time is homogeneous and isotropic, we have the well-known Friedmann-Robertson-Lemaitre-Walker type of metric, which is the following, which is completely determined up to 2 data, k, which is either 0 or plus minus 1, which basically tells us which is the local topology of the Cauchy surface, and a of t, which is the scale factor, which is conventionally defined as a smooth and positive definite function, which has to be determined only out of the dynamics, which means Einstein's equations. So recent observations suggest, but it's not a definitive statement, just suggest, seem to favor flat spacetimes, so k equals 0, and therefore we have that the spacetime is conformally flat, conformally Minkowski, and also seem to suggest that the cosmological constant is lightly negative, which often is stated as the de Sitter phase, but this has to, it has to be read only as the late time behavior of the universe, which means that for t going to infinity, or for large times, then the scale factor should be approximated with an exponential function. No, I have this one. So, as we all know, the standard cosmological model is plagued by many problems, ranging from the homogeneity problem, the initial singularity, and above all the fact that the universe appears to be in an accelerated phase. Well, the first 2 problems were known since ages, but thanks to the so-called Planck error, many people would just discarding them, saying, okay, the moment we will know quantum gravity, we will know how to solve also these problems. The third one is, in my opinion, the real killer of the standard cosmological model, because if you take the standard Friedmann-Robertson-Walker metric and the standard Friedmann equations, you would see that you need, if you assume that the matter is classical, as it is in classical cosmology, then you need a negative pressure in order to account for an accelerated phase, and this is not good, and because we don't know of many perfect fluids with negative pressure, and that led to, let's say, modern cosmology, leading to problems such as the fact that we might have dark energy, and furthermore we also know that nowadays that there exists a large amount of non-visible and also weakly interacting matter, which is cold, and this is so-called cold dark matter, CDM. So what is my point of view is that one of the big issues in classical cosmology is that no one has ever taken seriously that matter has to be quantized. Well, recently of course, but in the past not many people were taking seriously the fact that matter should be described by quantum fields. And what was the attempt in our papers was to try to take seriously that in a cosmological setting matter should be described by quantum fields using a mathematically rigorous approach such as the algebraic approach. So these, as I said, are our goals. So understand how to rigorously quantize field theories in cosmology, and this also entails that we need to understand whether a distinguished quantum state exists, because of course we cannot use the Poincare vacuum since we are not in Minkowski spacetime. Also the Bunch-Davies state is a good quantum state if you're working on the Sitter spacetime, exactly the Sitter, which is exactly what is not happening because we are not living on the Sitter spacetime. So, first thing I would like to stress is that although the algebraic approach to quantum field theory is a priori a way to construct quantum theories from, say, building blocks, what is really done from the practical point of view is to take a classical field theory and to quantize it. So it's a quantization of a classical field theory. It is never the construction of a quantum theory from first principles. Although many people in the community would tell you that this is our ultimate goal. Therefore, first of all, you have to take into account that in order to quantize a classical theory, you need a classical theory. And classical theories cannot be constructed on arbitrary spacetimes. Because we understand classical theories in terms of classical observables only when we know the space of solutions of the equations of motion of the theory, at least in principle, starting from initial data. And initial data can be assigned only if you have a Cauchy surface. And therefore we consider only global hyperbolic spacetime, which are four-dimensional differentiable connected Hausdorff spacetimes endowed with a Lorentzian metric G and an isometry from the manifold into R times sigma, where sigma is an embedded three-dimensional submanifold. The pullback of the metric can be written in the following form, where beta is a smooth and positive function, tau is a temporal function, and h is a smooth and Riemannian metric for each fixed value of tau. Then, when we know that on this spacetime sigma, any sigma plays the role of the initial value surface, now which kind of classical field theories do we consider? Well, in principle, all field theories could be considered, provided that the dynamics is ruled by a Cauchy problem. On practical grounds, this is a sort of tautology, and therefore we look for free field theories because their dynamics is ruled by a linear PDE whose principal symbol is normally hyperbolic, which means that the principal symbol is ruled by the metric, which means that will give us control on the causal structure of the theory, and interactions can be treated perturbatively. So there are, from a purely mathematical point of view, there is no known interacting model in four dimensions which could be called mathematically well defined. Not even lambda phi to the fourth. Actually, it's a good candidate for a model which is not going to be well defined. Now, what is algebraic quantum field theory? Algebraic quantum field theory is basically a program to quantize, is a scheme, if you prefer, to quantize a theory in two steps. The first step is to take a classical field theory and associate to this theory a C-star algebra of observables. And the second step consists of identifying a quantum state, which means a positive and linear functional. So you take a function from your algebra into the complex numbers, which is normalized and which is positive. Notice that this is a non-linear constraints on the choice of the possible states, and therefore it's very difficult to implement this constraint in concrete examples. Why are we happy with the quantum state? Because then you can invoke the so-called GNS theorem, Gelfand-Naimark-Siegel, which tells you that if you have a quantum state on a unital C-star algebra, then you can identify out of this state a Hilbert space, or actually a dense subset of a Hilbert state, on which your algebra is represented by means of bounded operators, if you have C. Well, otherwise it's only linear operators if you have a star algebra. And furthermore, you have also a cyclic vector, which is what plays, if you like, the role of the ket zero in the standard quantum field theory. So this part in algebraic quantum field theory, it's very easy. It's just a game, you know it, you have to apply standard rules and you know how to do it. This is instead the difficult part. So I will show you how to do it in a cosmological setting, and I've chosen scalar fields because they are always fashionable examples, though we don't know we haven't seen experimentally any scalar field yet. The key point is that my choice for scalar fields is just for simplicity. If you want, I can do it for Dirac fields, Procca fields, spin 2 fields, everything which is not spin 3 half can be done. If you have spin 3 half, then you are running out of luck, because there is a no-go theorem which tells you that there is no quantization scheme for spin 3 half fields unless you are on a flat space-time or you have a constant curvature space-time. So let's start with the scalar field. So we take a real scalar field whose dynamics is ruled by the following PDE. Basically, we consider a Klein-Gordon field with an arbitrary mass and an arbitrary coupling to scalar curvature. as we heard in previous talks, well, there is no real need to consider a particular, let's say, value for this coupling to curvature from the point of view of quantization. No value is favored. Actually, sometimes if you have psi equals 0 and the field is massless, then you cannot even quantize your field. So actually it's better not to have it 0. Particularly if you're working in the Sitter spacetime. So when you see this equation of motion, it's very easy to solve it because it's basically the wave equation, even if on a curved space-time. Therefore, you can construct all the solution as follows. Take any smooth and compactly supported function of your manifold. Then there exists a solution, which is a smooth solution of this equation, which is constructed as the causal propagator applied to this initial datum. The causal propagator is the difference between the advanced and the retarded fundamental solutions. If you prefer, you can call them the green operators, which are characterized basically by being the left and right inverse of P, which is the operator which identifies the equation of motion. And furthermore, and here it's important that you have the metric controlling the principal symbol. The support of your solution is contained in the union of the causal past and the causal future of the support of the initial data. If you're not familiar with this way of constructing solutions, this is totally equivalent to assigning initial data on a Cauchy surface. Namely, you could take any Cauchy surface, assign the value of the field on the Cauchy surface and its normal derivative on the Cauchy surface, and you will solve it in the standard way. And all the solutions you would obtain in this way are completely in one-to-one correspondence with the solutions you would obtain in this way. Now, there is a theorem which holds true basically for all bosonic free field theories. There is also a counterpart for fermionic field theories, which tells you that if you take the set of all smooth functions, which is a solution of your equation of motion, or in other words, there exists a smooth and compactly supported function on your manifold, out of which you can construct your solution in terms of the causal propagator, then this is a symplectic space, if endowed with the following weakly non-degenerate symplectic form. The symplectic form can be constructed out of the causal propagator with the following formula, but if you are used to work with Cauchy surfaces, then you can define it in terms of an integral over the Cauchy surface where you have the field and the normal derivative of the field. All these should be meant as, should be read as restricted to the Cauchy surface itself. These are smooth but compactly supported on Cauchy surfaces, so this integral makes sense and it's independent from the choice of sigma. Now, the reason why I told you that it's very easy to solve the first step in the scheme of quantizing a field theory from the point of view of algebraic quantum field theory, when you have a symplectic space, you have automatically a unique C-star algebra, and unique up to star isometries. This C-star algebra is constructed as follows. Take your symplectic space, then you can construct an algebra whose generators are basically the following abstract objects. So you assign an abstract generator to any solution of your equation of motion, and then you have to assign a star operation, which is basically sending the solution to minus the solution, and then you have to define an algebra structure, and the internal product is defined out of the symplectic structure. Here you realize why you need that the symplectic structure is weakly non-degenerate. If it were degenerate, you would have a center in your algebra, and well, in general, when you have centers, it's very bad. The first example where you have a center is a gauge theory. In that case, then you have to mod out the center or control the center, and that's usually a problem. But you can solve it, and therefore, basically, whatever field theory you consider, provided it's a free field theory, then you can easily construct a Weil algebra and therefore a C-star algebra of observables. From a strictly physical point of view, well, I would say that until 2001 this was the canonical algebra of observables of a quantum field theory, but it's highly unsatisfactory because certainly here you will never account for the stress energy tensor or the Hamiltonian, because they are not bounded from above. So here they are only bounded operators. And you want, if for example you want to solve semi-classical Einstein's equation, therefore you want to consider a quantized stress energy tensor, it's not inside here. So in general you would have to consider star algebras. So if you want to do real physics, you have to get rid of the nice property of being a C-star algebra. So for the sake of simplicity, I told you how to construct the C-star algebra, but there is a canonical way to construct a star algebra out of the symplectic space, so it's not really a problem until you work with free fields. Now, what is the problem is, well, the selection of a state. In general, there is a problem, because how do you construct a state? Well, you know to construct a state in Minkowski spacetime and in de Sitter spacetime, because you have basically the Poincare group and the de Sitter group, and out of these groups you can construct a unique vacuum state which is invariant under either the Poincare or the de Sitter group. Well, but in a generic curved background you don't have isometries, or not enough isometries to construct a unique state. Therefore you would like to know at least what is a physically sound state. There is a plethora of states around, you can choose a random one and you will see always disasters. So what is a physically sound state? A physically sound state is, well, known since the 70s to be a state which has the same ultraviolet behavior of the Poincare vacuum, which mimics the fact that in GR, if you probe smaller and smaller distances, you tend to probe a point, and at each point the metric could always be set to the Minkowski metric by a change of coordinates, and therefore from this point of view you expect that in the ultraviolet regime you will always see something which is similar to the Poincare vacuum. And
just a question about the C-star algebra. Do you have a natural group which checks on it?
On this one?
Yeah.
Well, basically only the group of isometries of the background, but that's all you have. Nothing more, nothing less, in the most general case.
Yeah. Okay.
That's why you have a problem to construct states.
Okay, yeah.
Exactly. But that's why now we will the trick is to embed this star algebra in a bigger algebra where you have an infinite dimensional group actually acting on it, and there you can construct a distinguished state whose restriction is invariant under all the isometries of the spacetime, and it's basically unique. So that's the trick. So furthermore, you want that quantum fluctuations of observables are bounded. You look in the literature, and these states are known as Hadamard states. Now, how do you characterize Hadamard states from a practical point of view? Well, until the 80s, 90s, people would tell you, first of all, we would like to work with quasi-free states. Those are the states which in cosmology are known as Gaussian states. This means that only that every correlation function can be completely determined out of the 2-point function, and therefore the 1-point function, 3-point function, so on and so forth are 0, and only the 2, 4, 6 and so on and so forth endpoint functions are different from 0. So then in this case you can look at 2-point function, and the 2-point function is in general a bidistribution on your manifold, and you would say that a state is Hadamard if on any normal neighborhood of the underlying spacetime the 2-point function reads as follows. It's u over sigma plus v log sigma plus w, where u, v and w are smooth functions. Sigma is the geodesic distance between x and y, therefore you have to work in normal neighborhood because there is a geodesic distance, and lambda is an arbitrary length which basically makes the logarithm dimensionless. Furthermore, you have to impose equations of motion because you want that the state solves your equations of motion in a weak sense, and if you do it, you realize that u and v can be completely determined out of the metric of the spacetime. So they are purely geometric data, so you have no freedom to choose u and v for a given spacetime with a given metric. They are completely fixed, and basically Seeley-Dewitt coefficients are known in Lorentzian spacetime as Hadamard coefficients, and they are all determined out of the mass, the coupling to the scalar curvature, and the metric of the spacetime, and they are all contained in this V and in this U. You can compute them, you know them, both U and V are perfectly well known. So the choice of a state lies only in this smooth function W. So choosing a state on a fixed space-time means that you are free to choose this W. Therefore, the singular part of a quantum state is completely fixed once you assign a space-time. This is useful because the moment you want to renormalize or regularize your theory, you don't have to think about the choice of the state you have done. You just say, I want a Hadamard state, and then the regularizations will mean subtracting the singular part, but the singular part is fixed once the geometry has been fixed. One could argue that here we have quasi-free states. It has been recently proven that if you take an arbitrary state, then the very same result holds true. You just need to control the two-point function, and the singular part is always completely determined out of the metric. Of course, if you work on the Sitter spacetime, Minkowski spacetime, it's quite easy to check on every normal neighborhood whether your state has this form or not. If you take an arbitrary global hyperbolic four-dimensional spacetime, you can have quite a few normal neighborhoods to check. So that was the practical reason why it was impossible to check whether a state was Hadamard or not. Until in, at 95, 96, it has been discovered that there is a connection between the notion of Hadamard state and microlocal analysis. Namely, you can control, since this two-point function is a bidistribution, you can control the wavefront set of a bidistribution, and it turns out that the state is Hadamard if and only if the wavefront set of the two-point function, so of the Schwarz kernel of the two-point function, satisfies the following form. So basically it's given by points in the cotangent bundle, in two copies of the cotangent bundle of the manifold, where you remove the zero sections, and the point x and y are connected by a light-like geodesics, which basically reproduces the fact that the principal symbol is controlled by the metric, and kx and ky are the vector tangent to the light-like curve connecting x to y, and kx is future pointing. So it's quite strange, but it's much easier for an assigned state to control the wavefront set than to control the form of the Schwarz kernel in every normal neighborhood. Now let's see in a cosmological spacetime how we constructed states. So we constructed states in the following way. As I told you, I'm working with Friedmann and Walker spacetimes with flat spatial section. And well, there are two immediate consequences. The first is the following. If you consider a co-moving observer as the integral line of dt, then if you remove the causal path of this co-moving observer to the manifold, and this is not empty, then causal signa which are departing from any point in this M where you subtracted this causal path will never reach per definition the causal path of this curve. Therefore there is a cosmological horizon. Well, it's known in cosmology, it's part of the particle horizon problem, at least it's related. And the other fact is that you can give a sufficient condition for an horizon to exist, and it's the following. If you work with the conformal time, therefore the metric is explicitly conformal to the Minkowski metric, then a sufficient condition for the horizon to exist is that if you call alpha beta the range of the conformal time on the real axis, so alpha has to be greater than minus infinity, and or beta has to be smaller than infinity. So you cannot have the whole real line. Well, our second hypothesis is the following. Okay, then let us restrict it to a class of scale factors which goes as follows. A of tau goes as minus 1 over h tau, where h is chosen positive so that the interval where tau is defined is minus infinity 0, plus something which goes as tau minus to minus 2, or the derivatives behaves in the same way, and the second derivative also behaves in the same way. So here goes as 1 over tau squared, and here as 1 over tau cube, and so on and so forth. Why is this important? Well, from a physical point of view, this has the following meaning. We consider only spacetimes which have a late time behavior which mimics the de Sitter behavior. So, at late times, so as tau goes to minus infinity, the backgrounds tend to be the de Sitter space, and therefore we are dealing with an accelerated expansion. Well, here I've chosen tau going to minus infinity. I could revert going to tau plus infinity, and I would have a late time de Sitter phase. So these are spacetimes which are supposed to be a good approximation either if you work with inflation or if you work at late times and where you assume there is a cosmological constant which accounts for a sort of de Sitter phase. Now, why are we happy about it? This is purely for geometrical reasons. If you're familiar with Penrose compactification, you know that Minkowski spacetime has of course has no boundary, but could be compactified in such a way to be embedded in the Einstein universe, and therefore, as seen as an open subset in the Einstein universe, it has a conformal boundary. Well, here we have something similar with an advantage. We don't have to rescale it because Minkowski has to be rescaled. Here there is already the rescaling, which is the conformal factor. As a matter of fact, since according to our assumptions there's always a cosmological horizon, we can change the coordinates exactly as you do when you compactify Minkowski spacetime. So you introduce the following U and capital U and capital V coordinates, and the metric becomes the following one. Then you can open your favorite book of GR, well, for example, Watt's chapter 8. It's standard reference for asymptotically flat space-time, bearing one or two mistakes here and there. Under the previous assumptions, you can prove that a Friedmann-Robertson-Walker space-time, which is asymptotically the de Sitter space-time, can be extended to a larger space-time, which is the conformal completion of an asymptotically flat space-time at past or at future null infinity. So the scale factor plays the role of the conformal factor, and therefore you can read the cosmological horizon as behaving exactly as a future or past null infinity in an asymptotically flat space-time. So what is the reason for doing this? From a mathematical point of view, there is no reason at all. From a physical point of view, if you are familiar with, well, let me maybe. No, eh? Well, I'll try to. So your space-time goes as follows.
Yes.
There is a better light. Oh.
There's a better light.
Yeah, better. Thank you. So this is the space-time I call M. It's inside here. This is the cosmological horizon, which I would call square minus, and you can embed this space-time in a larger space-time, which, let me call it at hem, which is globally hyperbolic and has a metric G hat, which restricted to this region coincides with the Friedmann-Robertson-Walker space-time. What is the idea? The idea is that if you assign me initial data here, which means a smooth and compactly supported function, you try to solve the wave equation. The wave equation will have support in the future and in the past. Particularly, since also the larger space-time is globally hyperbolic, the solution will have support here, but also here in the larger space-time. And therefore it makes sense to consider for every initial datum the restriction of the solution here on the cosmological horizon, or if you prefer on the boundary, and therefore to every solution in the bulk you will have a solution in the boundary. But the boundary will be a crazy boundary, so it will be a null manifold. You can construct a quantum field theory on the boundary, such that every generator of the Weyl algebra here is encoded in a generator of the Weyl algebra here, but since this is a crazy space-time, it's much easier to assign states whose pullback in the bulk will turn out to be Hadamard. So the idea is solution in the bulk implies solution in the boundary, which means algebra of observables in the bulk is a subalgebra of an algebra of observables on the boundary. And then you can pull back states. Well, why this can be done? First of all, because conformal null infinity, or the cosmological horizon, which corresponds in this diagram to region C, this is the conformal diagram of a Friedmann-Robertson-Walker spacetime, is a null degenerate manifold which has the following, with a metric which has the following form. So it's degenerate along one direction, and basically there is the standard metric of the two-sphere in the other directions up to a constant. Therefore, topologically, null infinity is R times S2. Well, this is nice because if you have R, it means that you have Fourier transform along this R direction, exactly because there is no metric which prevents you from Fourier transforming along the R directions, because rigid translations R along the R directions are anisometry of this metric. Furthermore, the vector field detour is also of the Friedmann-Robertson-Walker metric is a conformal killing field for the metric G hat, so for the metric in this larger space-time. And when you gets to scribe plus and minus, it becomes tangent to it, and it coincides with the following form. Well, sounds like okay, it's a curiosity, but it will turn out that it will be possible to, thanks to this fact, it will be possible to determine a unique state on the boundary. Now we want to model a scalar quantum field theory on a cosmological space-time and to find a distinguished ground state. How can we do it? First, we have to better characterize the space of solutions. Well, since we work on a Friedmann-Robertson-Walker spacetime, so we have R3 and with flat spatial sections, and we have R3, then we can decompose in modes every solution, and the modes in particular are characterized by the following functions, where there is this function chi, where chi is a solution of a differential equation, which in a Friedmann-Robertson-Walker spacetime is quite ugly because it depends on the scale factor. So the trick is the following. First, you consider that your scale factor is the de Sitter 1, and this gives you a potential which I call V0, and which has the following form. Then whatever is left from A of tau, we know that asymptotically tends to de Sitter, so is of order 1 over tau cube, and we consider it as a perturbation potential. Then we try to solve this equation as a perturbation series, and we have to prove convergence of the perturbation series. Furthermore, the following normalization condition holds true. So, as I told you, this is the general idea. Construct the solution as a perturbation, because in de Sitter we know exactly how the wave equation can be solved, and these mode functions are basically the Hankel functions, so they can be constructed up to, let's say, a phase. This phase depends on an index index nu, which is constructed out of the mass, the scale this h, which appears in the metric, and the conformal and the coupling to scalar curvature. Now you have to construct the perturbation series. So you take the unperturbed equation of motion, you construct the retarded fundamental solution, you call it SK, and then you construct the standard, well, it depends. If you're a mathematician, Duhamel. If you're a physicist, Dyson series, that's the same. And this is basically, you start constructing integrals over integrals, and then you start to make estimates over estimates, and you discover that the series is actually convergent. So if the real part of this factor mu, so this factor mu depends on the mass and the coupling, basically for all possible potentials, so they have to be of order tau of to the minus 3, whereas if you work in the range between 1/2 and 3/2, they have to be of the order tau to the minus 5. Notice that 3½ is excluded exactly because 3½ would be the case of a massless, and minimally coupled scalar field in the zeta spacetime which admits no Hadamard states. No Hadamard state whatsoever, so in that case there is no good quantization scheme. So, in the bulk we have our Weil algebra, so we have the space of solutions, we have the Weil algebra, and which is constructed out of the generators with these relations. Now, what can we do on the boundary? Of course the boundary is null, so there is no dynamics, but we can nonetheless assign a symplectic space on this boundary, and therefore we have, once we have a symplectic space in the boundary, we have a Weil algebra in the bulk. On the boundary. So which symplectic space do we construct? We assign the space of smooth functions on the boundary, which are L infinity, whose derivative along the r direction is L1, and similar conditions on the Fourier transforms along the r directions. This is a weakly non-degenerate symplectic space, and therefore we can assign to it a Weil algebra, assigning a generator to each of these elements in the symplectic space, where the star operation is the same as in the bulk, and the algebra is defined in the same way out of the symplectic form. First question one should ask, why this symplectic space out of the zillions of symplectic spaces which are existent on the boundary? Well, for one simple reason, it is the unique, it's a unique one which will fulfill an important property, namely, I will show you in 2 slides, namely there is a symplectomorphism between the symplectic space in the bulk and the symplectic space in the boundary. Every other choice would have failed to yield the symplectomorphism between the 2 symplectic spaces. So the choice is unique for this reason. And we went to symplectomorphism because we want to control the bulk algebra out of the boundary one. But first of all, why we like the boundary state? We like the boundary space because it has a distinguished state. So we can assign a distinguished state to the Weil algebra on the boundary by means of a Gaussian state, and the Gaussian state can be constructed via modes. This is good because, well, people want to work with modes, and this is the standard theta function, and this is the Fourier-Plancherel transform along the r direction. And this is basically the form of the state, which is the one we are used to see in, say, in all quantum field theory calculations done in cosmology. One can prove that the state lambda, is quasi-free, it's pure, and it's invariant under the left action of the horizon symmetry group, which is basically a subgroup of the Bondi-Metzner-Sachs group, if you know the Bondi-Metzner-Sachs group. Otherwise, it's a semi-direct product between SO3 and the smooth function, so over the 2 sphere taught as an abelian group under addition. So it's an infinite dimensional group. Well, furthermore, there are other properties which are making always happy my colleagues working in, as I call it, pure algebraic quantum field theory. Namely, you can prove that the state is, lambda is a unique, quasi-free, pure state, which is invariant under rigid translations along the boundary. So you just need to control translations along the boundary, along the null direction, the state is unique. And in its genus, this leaves fixed the cyclic genus vector, it's strongly continuous, and it has a non-negative self-adjoint generator. So it's everything a pure algebraic quantum field theorist would like to have. And in each volume of states, on the Weil algebra on the boundary, there is at most one of these states. So basically you have a sort of uniqueness, what you would call in algebraic quantum field theory, uniqueness property for the state on the boundary. Now, the reason why we like it from the bulk point of view. If you take the symplectic space in the bulk, and so you take any solution or any element of the symplectic space, for the reason I've shown you here, this can be extended to a unique smooth solution of the same equation on the larger space-time, so this one, the bigger one, and therefore it makes sense to consider the restriction of the solution to the boundary itself. And this is a smooth function because all solutions are smooths themselves. And now you prove the following theorem. It tells you that if you have a solution and you have basically every value of the mass or of the coupling of the scalar curvature of the coupling of the field with the scalar curvature excluded the massless and the minimally coupled one, then this field on the boundary decays as faster than 1 over L to epsilon, where epsilon this, and its derivative faster than this. And for this reason, you can prove that the projection of the field to the boundary is an element of the symplectic space on the boundary, and that there is a symplectomorphism up to an irrelevant constant, this h is just a numerical constant, between the bulk symplectic form and the boundary symplectic form. Therefore, you take a generator of the Weyl algebra in the bulk, and you can project it naturally to the generators on the boundary, because you take the generators with the projected solution, and this is an isometric star homomorphism. So you can see the Weyl algebra in the bulk as a subalgebra of a very large algebra, which is the algebra on the boundary. So any state on the boundary can be pulled back to a state in the bulk, because, and this applies particularly to the preferred state on the boundary. We have done it, and then we checked we checked the result. What are the properties? Well, first of all, you work in the Sitter spacetime, which is a subcase of our class of spacetimes, and you get exactly the Bunch-Davies state. So you get the state you would like to have. Otherwise, it would have been totally useless. Lambda m is actually what the cosmologists should consider as the correct ground vacuum state in the study of linear perturbations, because if you're not working exactly in the Sitter, then you're working in something which is fluctuation over the Sitter spacetime, then this is the spacetime you're working with, and this is the Hadamard state you should be working, because this is the unique ground state you would have. Furthermore, it's invariant under all the natural actions of the bulk isometries. So you have an isometry in the bulk, you have your Euclidean group, for example on the Cauchy surfaces. This is implemented exactly on your quantum state, so no problem. Well, and then in terms of time translations, also then the one parameter group of the action of the time translation is positive self-adjoint operator, which is a good candidate when you want to talk of Hamiltonians.
Generator, really?
Of the geometric action of the translations. Well, this is not important unless, well, you can prove that that the state is Hadamard. Now, this is actually the Schwarz kernel of the two-point function of the state I've constructed. One can compute it. And one has to prove the following theorem, that the wavefront set of this state is actually of Hadamard form. So its wavefront set has the form I've shown you before. Okay, this is not easy. I could skip the proof, but just to give you a flavor of how things are done, without going into the details, basically you prove a double inclusion, first in one sense and then in the other sense. This inclusion is the easiest because you know that your state fulfills the equation of motions in a weak sense, and its antisymmetric part coincides with the causal propagator. So you can use the theorem of propagation of singularities of Hermander to prove that if you can prove the other inclusion, then this inclusion also holds true. The other inclusion is quite a mess. So first of all, you have to introduce the following bidistribution on let's say this scry minus times scry minus, so boundary times space-time times space-time, and then you have to introduce a sequence of cutoff functions which are smooth and compactly supported on the boundaries, such that the following sequence converges to your state with respect to the Hermander pseudotopology. And this is quite a problem to prove. Then you need a last theorem. When you have the sequence, you have to prove that also the wavefront set of your sequence is contained exactly in the wavefront set you want, provided, of course, that the convergence of your sequence of states to the states you like is in the weak sense in the distribution. And then you start crying, because you have also to prove that basically taking any cone closed in the cotangent bundle lying in the complement of wavefront set, you can control the following supremum. You do it, takes usually between 6 and 9 months, and then you know that your state is Hadamard. But at least you have Fourier modes, and if you have Fourier modes, you can do explicit calculations. Well, the summary is it might be a nice result provided it's useful. Well, is it useful? I will try to convince you in the next talk it is useful from a physical point of view. Namely, we can obtain numbers. Notice that up to here the state is constructed at 0 temperature, and we would like to have a state instead a certain temperature. This is no problem, you can do it. You can do it for same construction for Dirac fields, you can do it for Maxwell's equations, so for the vector potential, for Proctor fields. No matter which field you are interested in, you can do it. Now the problem is, are there interesting properties which can be proven with this state? Next talk for this. Now, since I didn't know exactly the schedule of the talks when I prepared them, I suppose that maybe someone might have not heard the first talk, so I will summarize what I've told you in 1 second now. It was supposed to last a few minutes. And then, well, the outline of the talk is the following. So we will start from the distinguished states in Friedmann-Robertson-Walker spacetime, and I will show you that it's possible to compute the expectation value of the regularized stress energy tensor for, in this case, about a scalar field, but for whatever free field you like. And what the idea is that, okay, let's see what is the effect of semiclassical Einstein's equations in a flat Friedmann-Robertson-Walker spacetime. So we want to solve exactly semiclassical Einstein's equations in Friedmann-Robertson-Walker spacetime, assuming we have a Hadamard state of the form I've shown you before, considering the regularized stress energy tensor. This goes along the lines of what has been done by Starobinsky in the late 70s, early 80s, when he studied the conformal anomaly, but it's completely different because at that time the result is completely different because at that time the machinery of Hadamard states and regularization in curved space-time was not known as it is known nowadays, and therefore the result that the Sitter phase is unstable, which this was the result of Starobinsky, turns out not to be the case if you consider Hadamard states and the algebraic approach to quantum field theory. And as a last step, I will therefore develop the solutions of semiclassical Einstein's equations and compare them to experimental data and show you the plot. So basically how the theory behaves when you compare it to supernova data, the baryon acoustic oscillations, and so on and so forth. This is based on papers I've written with Klaus Friedenhagen and Nicola Pinamonti, Thomas Paul Hack and Jan Müller, these all from Hamburg, at least in that time, and the paper I've written a few months ago with still Thomas Paul Hack and Nicola Pinamonti. So this is what I told you. I'm considering a Friedmann-Robertson-Walker spacetime with flat spatial sections, and the dynamics of the scale factor is ruled by Einstein's equations. Well, the point is which T nu mu? Well, in textbooks the stress energy tensor, which is always considered, is, for good reasons, even the stress energy tensor for a classical perfect fluid. Yet, as I told you before, I want to take seriously the idea that matter should be described by quantum fields, and these should be analyzed within the framework of quantum field theory and curved spacetime. But if you believe that quantum fields are really the good candidates to describe matter even at a cosmological level, then you might try to solve the semiclassical Einstein's equations. Of course, one would say, okay, this is not a well-defined sense. How could you know that this theory makes sense, or the semiclassical Einstein's equation? Of course we don't know, but since we don't have a full quantum theory of gravity out of which to compute the limit and see if we are right or wrong, we can just try and see what's coming out and try to, decide from the results if we like it or not. And if we think that a good quantum theory of gravity and all matter fields together should have as a limit also semiclassical Einstein's equations. So So the following questions are necessary to address the problem of semiclassical Einstein's equation. First, you need to find a natural state to be used in cosmological spacetimes, and this is something we answered already in the first talk. Then we have to find solutions of semiclassical Einstein's equations, see if this late-time cosmological evolution arising from these equations is compatible to what we are nowadays observing, and then we want to compare it. Okay, is it really better to use quantum fields rather than lambda CDM? Well, for lambda CDM I mean that the cosmological constant is really a constant of nature. We don't know from where it's coming from. It's like h bar. We have to assign it no matter what. And then there is matter, which is cold and not interacting with all other fields, which is cold dark matter. And this is the model which is used nowadays when you see all these nice plots come up with supernovae and so on and so forth. And if there is a difference between what quantum free fields are predicting and lambda CDM, well, this has to be experimentally accessible, otherwise it's completely moot. Because if we cannot ever measure it, well, then no one will tell whether this model or the other model is better, and since the other model is certainly much easier, then use the other model. Okay, as before, I will work with global hyperbolic spacetime, so scalar field here, but take into account that actually we had to repeat all the calculations also for photons, so for the vector potential as well as for Dirac fields, because in our model we had to account also for fermions and of course for massless photons. As before, the space of solutions can be constructed out of smooth and compactly supported initial data by applying the causal propagator, which is the difference between the advanced and retarded fundamental solution, or green functions, which are left and right inverse of the wave of the Klein-Gordon operator, and the support of the solution is contained in the causal past and the causal future of the support of the initial datum. Now, since we want to stress energy tensor, no more Weil algebras. Weil algebras do not contain T nu mu, so we have to work with something else, which is not a C-star algebra, but rather a star algebra. And well, if you have free fields, this is not difficult. It's the algebra of fields, which is constructed as follows. First, you take the universal enveloping algebra, or the tensor algebra, if you want to call it, out of the initial data. So take C infinity of compactly supported functions, and then construct the following algebra via tensor products. And you assign an involution, which is given by complex conjugations. Well, sometimes this algebra is also called the Borchers-Ullmann algebra, because it's not the tensor algebra, because there is also this involution. Okay, well, it's basically the tensor algebra. Yet the problem is that it doesn't contain any physical information because it doesn't encode dynamics. To encode dynamics, you have to single out an ideal which is generated by elements of the form ABC, with AC in the algebra A you're starting from, while B is of the following form. This form, and this form basically just the star operation, the linearity of the algebra. Then this tells you that the equations of motion are satisfied in a weak form, whereas this is, which is the commutator between two algebra elements, tells you that the commutator is proportional. Well, it's a C number times the identity operator, where the C number is proportional to the causal propagator, applied to the test functions generating, of course, the two observables f and phi f and phi of f prime. This is a star algebra, and a quantum state has to be defined actually on this star algebra as before, so as a continuous linear functional, which is, sorry, I forgot to say, it's normalized to the unity, and it is positive. So this is the important, let's say, the important condition. In physical scenarios, we always want to work with Gaussian states because they are easier, and they are completely determined out of the two-point function, which has the following form. As before, on cut space-time, we don't have a unique choice for such a state, and we cannot work with the Minkowski vacuum, but we want something which mimics its properties in the ultraviolet behavior, and this quantum and the quantum fluctuation of all observables are bounded. Good? we do it in Friedmann-Robertson-Walker spacetime as before, and I want to stress that we consider only spacetimes which are asymptotically de Sitter, and therefore possesses, each of these spacetime possesses a conformal boundary. The distinguished Hadamard state has the following form, which is the one I've shown you before, but with a subtle difference. There is a Bose factor here, when you have to insert this Bose factor because you can prove that this is a KMS state on the boundary, an exact KMS state, and if beta is 0, it is still the Bunch-Davies state in the bulk. It is invariant under the natural action of any bulk isometry, and it's of Hadamard form. Well, it's very easy to prove. You just subtract the two-point function of with beta equal, so with 0 temperature. Oh, sorry, here it's beta equals 0, it should be t equals 0. Sorry, t equals 0. So you subtract the two-point function at t equals 0, and you see that the waveform set of this difference is empty, therefore the difference is moot. Therefore, if the state you're starting from is Hadamard, also the state with the Bose factor is Hadamard. So this is very easy to prove. And in the bulk, it's not. Yeah.
Yeah. Could you repeat again why this appearance of theta of k?
Oh, positive energy, because you have you are doing it's the equivalent you would have about selecting positive energies, because you are transforming, you are Fourier transforming along the null direction r, and the rigid translation along r plays the role of the time translation on the boundary. Actually, if in the bulk the time translation, for example, would be an isometry, then it would project exactly to this rigid translation on the boundary. And therefore, when you construct a state, you want to select positive frequencies or positive energies, and this is the reason why you want theta of k. Exactly as you do for the Poincare vacuum, that you have theta of k. Now the state is of Hadamard form also, but it's not always thermal, because to be thermal you need, either you need a time-like Killing vector field in the bulk, which is certainly not the case in Friedmann-Robertson-Walker spacetime, or you can make sense up to conformal rescaling of a thermal state for massless conformally coupled scalar field theories. This is what people are implicitly doing when they are talking about the temperature of the cosmic microwave background. You cannot talk about temperature if you don't have a notion of temperature, which for quantum field theory means KMS states. Yet, since photons are solutions, basically, quotation marks, of Maxwell's equation, and Maxwell's equation are conformally invariant, you have the KMS state in Minkowski spacetime, and then you can conformally scale this state in Friedmann-Robertson-Walker spacetime and set it at the temperature you see of the cosmic microwave background. That would make sense of when talking about temperature. And that's exactly, if you do it for photons, not for scalar fields, you would exactly obtain this state. So it's compatible with the states you use when you are working with thermal field theory. Well, when you don't have a KMS state in the bulk, because you have a massive fields and you have massive neutrinos, for example, and then you can show that you can give an approximate thermal interpretation, at least the state restricted to a Cauchy surface at a certain time, as is exactly a thermal state. Why you want to do this? Because people are talking about the neutrino background temperature, but neutrinos are massive and they do not admit KMS states, so it makes no sense, strictly speaking, about temperature. But with this state you can make at least give an approximate notion of temperature. Otherwise, I wouldn't know how to make sense of the neutrino background temperature. Furthermore, also when you talk about cold dark matter, if you read cosmology books, they would tell you, well, cold dark matter is basically matter which is weakly interacting with everything else, but it's cold in a sense that it freezes out at a certain temperature at a certain time. So it means that at that time, at that value of t, you will have to make sense of the notion of temperature from dark matter, and if dark matter is not a conformally coupled scalar field, and it is not, because it has to be also massless, then what does it mean saying it's in a thermal equilibrium and it's a very low temperature at a certain instant of time? And therefore that was the reason why we tried to study KMS states, or at least approximate KMS states in cosmological spacetime. Now the second problem is that when you want to talk about the stress energy tensor, you have to talk about phi squared, so the squared of your scalar field, or your Dirac fields, of your Broca fields, or vector potential. But usually there are, well, always there are singularities, so you have to regularize. So in curved space-time, of course, you cannot do the normal ordering. You don't have A and A daggers, so creation annihilation operators out of which you can construct normal ordering, as you are doing in Minkowski space-time. But there is a way to, which is known in the literature, to regularize product of fields, which is called a Hadamard regularization, which in Minkowski is exactly the same as the normal ordering, which is the following. If you remember, in every normal neighborhood, and you can work in normal neighborhood because the problems are at coinciding points, so they are basically local problems, you are not interested in the large-scale behavior of your state, so it's okay to work in normal neighborhoods. Then the state can be separated in so-called Hadamard parametrics, which is the singular part, which depends only on the geometry, plus the smooth part, which is the choice of the state. So the regularization can be done as follows. You take the product of two fields at two separated points and you subtract the Hadamard regularization. It's nothing but point splitting. This limit defines the weak product of two fields, or if you prefer the squared scalar fields in a curved space-time, and it is independent of the choice of the state, provided that the states you are considering is Hadamard. The definition is well posed from a microlocal point of view, so no problem with wavefront set and microlocal analysis, but it's not unique. For example, you remember when I was writing this h, there was a log term which contained length, this lambda, to make the logarithm dimensionless. Of course, you are free to choose another lambda, and then your Hadamard state would change by something which goes as v of x epsilon log lambda prime over lambda. So you have a freedom in choosing this v part of the Hadamard parametrics up to smooth functions, and this is basically what you would call a regularization ambiguity. In the coinciding point limit, this regularization ambiguity depends only upon geometric terms, particularly the curvature or the powers, so r squared, r nu mu, things like that. So this regularization is unique up to local geometric terms. All these geometric terms would disappear in the Minkowski limit, so in the standard scenario you would not see them. And furthermore, you can prove, since you have to cope with derivatives with the stress energy tensor, that this can be extended to all derivatives of all fields in a natural way, no problem with that. Then you have all the ingredients to compute T nu mu, and first of all you realize that T nu mu is completely determined up to a freedom which is the following. You have four terms which you cannot fix a priori, one proportional to the metric, one and to the square, to fourth power of the mass of the field, one to the Einstein tensor and to square of the mass, one to I nu mu and J nu mu, which are of Lagrangian origin, which are these terms. And therefore you can take the stress energy tensor of your scalar field theory and compute its regularized form, and then take an Hadamard state, compute the expectation value, and you would like it to be covariantly constant, because the Einstein tensor in the semiclassical Einstein's equations is covariantly constant. So if this is 0 but this is not 0, then you have a problem of consistency with the semiclassical Einstein's equations. Well, it's never 0. There is never one single T nu mu for any free field which is covariantly constant on any Hadamard state. Well, not a big issue, because this has been solved. Actually, you can introduce the so-called improved stress energy tensor, which is unique. There is a unique improved stress energy tensor because you have the freedom to always add the metric times a constant times something which is proportional to the equations of motion, because on shell this is conserved, well, this is traceless and conserved, and therefore this term doesn't play any difference from the point of view of the classical dynamics, but from the point of view of the quantum theory, the expectation value of these terms and these terms are not 0, so they could change something, and as a matter of fact, if you choose this constant to be 1/6, then this modified or improved stress energy tensor is conserved, even if you work with thermal states, no matter the state you are using. It has to be Hadamard. Yet there is a price to pay, even if you would have considered a traceless stress energy tensor. In Friedman, Robertson, Walker, when you consider the improved stress energy tensor, you get a term where we get a correction, which is the so-called conformal anomaly, which has the following form, which, as you see, depends on h dot, h squared, a to the fourth. Then there are some constants, which are, because there is a regularization freedom in the stress energy tensor, this alpha m squared, gamma m squared. And then there is this term, which is a delta, which is a constant, which is still coming out of actually these two terms, this and this, because if you take the trace of these terms, this is exactly box of R, and box of R is a term which contains the third derivatives of the Hubble function. And when Starobinsky studied his model, he didn't have this delta, nor this alpha, nor this gamma, because he didn't account for the renormalization freedom. And that was his problem, because we know from, I think it's called Ostrogradski theorem, that in a dynamical system with derivatives higher than the second, you cannot hope for a stable solution. And therefore he concluded that even if there is a de Sitter phase for a quantum field, on account of the conformal anomaly, this de Sitter phase is not stable. This is true if and only if you don't account for the renormalization freedom. Otherwise, you have constant to play with, and therefore things are changing completely. Furthermore, if you consider a massive field, then you have to consider also the expectation value of the squared scalar field. And this, of course, depends on the choice of the state. So the state enters in this term. So if you consider massless fields, then you will never see any dependence on the quantum state. Only if you have a massive field, you will see that your trace anomaly depends on the quantum state, and therefore the solution of the semiclassical Einstein equation depends on the choice of the state. Now, let us go to a general scenario where we take not only scalar fields, but we take an N0 free conformally coupled scalars of mass m. Why conformal coupling? Because I don't want to write all the term with psi minus 1/6. If you want an arbitrary coupling, you can, and it doesn't change anything. It's the same. Where there is m squared, there is an m squared plus psi minus 1/6, a certain power of h, but everything else is the same. Then you can take a certain number of free Dirac fields of mass m. For simplicity, all the fields have the same mass, but also this is not to have huge formulas. And then you take n1 massless free spin 1 fields A, so basically photons. Then the conformal anomaly, the quantum trace of the stress energy tensor has the following form. So there is a dependence on the state for the scalar field and for the Dirac field, but not for the photons, because they are massless and therefore they are not dependent on the state. Now we want to look at the semiclassical Einstein equations, and we want to solve them. First of all, we look at the conservation equation. So the quantized stress energy tensor has to be conserved, and this entails a Friedman-like equation where in place of the standard energy density you have the regularized quantized 0,0 component of the stress energy tensor.
Yeah, in F you have coefficients in front of you, different field. Do they mean something?
You mean this n0, n1/2, and 1? These ones?
Yeah.
Yeah, this is the number of scalar. We admit arbitrary numbers of scalar fields, arbitrary numbers of Dirac fields, arbitrary numbers of photons a priori. These are, no, they are DD62, and no, this is just for computational reasons. This is on account of how you define the Hadamard parametrics, which comes with all these 2 pi's squared and it's all conventions that have no physical meaning whatsoever. You can always change these numbers as you like by changing the definition. So Now, if you look instead, well, this is the Friedmann equation, but now you can look at an evolution equation for this rho, and this is the effective Friedmann equation, which basically tells you that the derivative of this quantized T00 component is completely determined out of the quantized trace of the stress energy tensor. Now you want to compute it, well, it's a mess, and then you have to, here you have a huge, it's an ODE, but you have to make some assumptions. First of all, we use the thermal state we constructed, and we make the following approximations. So we say that the Hubble parameter is much smaller than the mass, which basically means we discard terms going as h to the 5 in the energy density. We say that the derivative of h is much smaller than the squared of the Hubble function, so we have a slowly varying Hubble parameters. And then we say that we have cold dark matter, which is consistent with experimental data, so the temperature is much smaller than the product between the scale factor and the mass. Now you can solve, this is an ODE, you can solve it, and the solution reads as follows, where these are coefficients C1, C2, C3, C4, C5, C6, which are completely arbitrary. Well, depending on the initial conditions, of course. Now, but what you're interested in is the Hubble function. You can consider the Hubble function, and the Hubble function depends, well, as the following form, where h star depends on the number of fields and on the renormalization freedom. C1 is an integration constant. Then you have C2 and C3 actually depend on the mass, on the temperature, and the scale factor at the time when the dark matter decouples completely from all other fields. And C4 is a renormalization freedom. So overall 1, 2, 3, 4, 5 parameters. So the plot of the solution is the following. You have two solutions, basically, where here it's on y there is h over this h star, and here there is t over h star, just to have adimensional units. And as you can see, both solutions are stable, and they are flowing towards a late de Sitter solution. This one you can fine-tune the renormalization constants in such a way that this one flows to a stable Minkowski solution, but you have always a second solution which is only of quantum nature, and this second solution flows always to a de Sitter stable solution. Here I cut the solution because here there is no way, well, here it's where our approximations are fading, and therefore we don't know if the solution is valid. Here I've drawn the whole solution because there is a recent paper from Nicola Pinamonti where he proves that there is a late time solutions for, well, this what we call this upper branch, and this is a smooth solution which flows for early times to a sort of power law inflation here, and at late times it's just a stable de Sitter solution. Now, okay, so we have two solutions. Now, so we have h as a function of time. Can we compare it with supernova data? This is a plot we have done in 2000 with data from 2010. Now you will see two lines. So the dashed line is the upper branch. So this one is the dashed line. The lower branch is instead the other line, so the continuous line, and there is also the experimental data from lambda CDM, but you cannot see it because they overlap exactly the lower branch. Well, there is of course a mathematical reason we will see in 1 second. Just another plot you can compute is the effective equation of state, so the ratio between the quantum pressure and the quantum energy density. Also here you see that the upper branch does not have a significant matter-dominated phase, which is this one, because you know that, well, you know, people from cosmology tell me that it's in order to have formation of large-scale structures, then you need that the equation, this factor omega q, so this ratio has to be at least larger than minus 1/3 for a long, long time. And the lower branch, well, doesn't create any problem, while the upper branch does, in a sense, seems to be not favored. There is another, let's say, observable, which has been introduced by Starobinsky, and he insisted that we could check it. We checked it, and this is called the OMZ, and it's very sensible to little variations in terms of z of the Hubble function. And as you see also here, the solid line is the upper branch, which varies considerably as in terms of z, whereas the dashed line is the lower branch as well as lambda CDM. What is the reason for this consistency between the lower branch and lambda CDM? The reason is that if you do the best fit of your parameters, you see that you can expand this formula in powers to the h star to the -1, this formula, and you realize that basically quantum fields account for these terms. K0, a cosmological constant, K3 over a to the cube, a matter term, K4 to the a4, a radiation terms, plus higher corrections, where K to the 5 is order of magnitude smaller than the others. But these data are not a priori fixed because they do depend on the renormalization freedoms. Therefore, one of the messages is quantum field theory on curved spacetime will never and never predict 120 order of magnitude discrepancy between theory and measured data. Quantum field theory on curved spacetimes does not predict any single value for the cosmological constant. There is renormalization freedom going on, and whatever field theory you will consider, you will never get a firm number. There will always be a number you have to measure out of experiments. That's if you take Hadamard states and the standard regularization for the observables, since you have to account for renormalized and regularized observables, there will never be a fixed value for this K0, no matter which quantum field theory you will ever take. So no 120 order of magnitude discrepancy. Basically, there is no number at all coming out of quantum field theory. This, for us, cosmological constant is something you have to measure out of the data because it's like a renormalization freedom. You have to measure it. So this is basically what I wanted to tell you. We have a natural choice for ground for thermal states for every free field theory in free normal work space-time. And after all interactions we know how to cope with are interaction treated perturbatively. So you need first to select a state and a free field theory on which you want to do perturbation theory. No spin tree off. There exists explicit solution of semiclassical Einstein's equation, which was thought not to be possible, but it seems that luckily enough it's possible. The lower branch displays a behavior compatible to experiments similar to lambda CDM. Well, in a sense, because this is lambda CDM. Lambda CDM tells you that you have a cosmological constant, you have cold dark matter, and you have radiation. The corrections are so small that you cannot see them at low z, and the supernovae are seen up to 1.7 z, so no way that for small z you can detect correction. You have to go to baryon acoustic oscillations or even to CMB in order to try to detect real corrections for a quantum field theory in a cosmological setting. Low z, no hope. There is no difference. Basically, the lower branch, this lower branch is the old-fashioned way of saying that quantized fields are a fluctuation over classical fields. This is basically what's going on here. Quantum fluctuations are negligible or very small, and therefore you don't see any pure quantum effect at low z. The cosmological constant appears as a pure renormalization freedom, no prediction on its size, no way. And free fields in the thermal state T0 display a component, which is this K3 over A cube, which mimics that of the cold dark matter. We are not saying that quantum fields we have are enough to explain dark matter. We say that dark matter could just be a normal quantum field. We don't need anything exotic in order to account for its behavior. Of course, it can be something we have not observed yet, so a new field, but it can be just one normal scalar field, direct field, or whatever. Now what it has to be done is, of course, go at a level of interaction, improve our understanding of quantum correction, and the real challenge is to look at semiclassical Einstein's equations in spherically symmetric spacetime, so you have 2 degrees of freedoms on account of Birkhoff's theorem, and that's really, really difficult because the equations are getting much more complicated. And of course, that's the general problem of algebraic quantum field theory. We have to understand how to include interaction, even perturbatively, and with understand, I mean also know how to do computations in terms of real numbers, not only in terms of theorems. Actually, we have to do both. And that's all. Thank you for your attention.